Welcome to our second lecture in our series on quantum mechanics. In the first lecture, we talked about the origins of quantum mechanics. We talked about how this theory was born. We talked about how Max Planck proposed the idea of quantization to explain black body radiation. We then talked about how Einstein used the idea of quantization and was able to explain the photoelectric effect. In today's lecture, we will continue to talk about history of quantum mechanics. We will see how other scientists use the ideas of Planck and Einstein to explain other physical phenomena. So we will start with Niels Bohr and how he used the idea of quantization to explain the structure of the atom. We will then see how de Broglie proposed the idea of matter waves. In the first lecture, we had talked about the wave-particle duality in the case of light. We will extend that idea further. We will then briefly talk about the very famous Heisenberg's uncertainty principle, and then briefly talk about the Schrodinger equation. At the end of this lecture, we will see how all these ideas combine together to create a coherent theory that we now know as quantum mechanics. In 1911, Rutherford came up with his model of the atom. His model of the atom was based on some very ingenious experiments that he had done. The experiments showed him that the mass of the atom was not uniformly distributed and the charge of the atom was not uniform. So he proposed that there is a central nucleus which contains most of the mass and all the positive charges, and around that the electrons revolve in orbits. The inspiration for this model came from the model of planetary motion. However, this model of the atom had certain deficiencies. According to Maxwell, any accelerating charge should emit radiation. Now, these electrons are accelerating because they're revolving around the nucleus. So they should be radiating energy according to Maxwell's equations. As they radiate energy, they would become less energetic and would therefore plunge into the center. Their orbits will become smaller and smaller and they will spiral into the center. A rough calculation shows that in about 10 to the power minus 8 seconds, all the electrons would plunge into the center. But we know that atoms are stable. The world that we see around us is based on the fact that atoms are stable. And the stability of the atom could not be explained by Rutherford's model. Rutherford's model also showed that radiation would have a continuous spectrum. So any orbit is possible in Rutherford's structure. So that means that any frequency of radiation is possible. Also, as an electron spirals into the center after radiating energy, while spiraling, it would emit radiation of different wavelengths and frequencies. Therefore, the radiation that would come out of an atom should have a continuous spectrum. But Max Planck had shown that radiation is quantized, that is discrete, that very limited number of frequencies are possible. Max Planck had shown that only multiples of quanta can be radiated by an atom. So Rutherford's model of the atom had these deficiencies and was soon discarded. In 1913, Bohr modified Rutherford's model of the atom and was successfully able to explain the hydrogen atom. Now, Bohr's extensions to Rutherford's model were arbitrary and lacked a physical basis. Now Bohr agreed with Rutherford that all the mass and positive charges were concentrated in the center, in the nucleus, and electrons revolve around the nucleus. However, Bohr said that these electrons orbit in stable orbits, or they revolve around the nucleus in discrete stable orbits. That means these electrons do not radiate. This electron can be revolving around this nucleus forever without radiating energy. Now, this idea was against Maxwell's equations. So this was more of an arbitrary proposal or assumption. Bohr also said that the orbits that are available are the ones in which the angular momentum is quantized. That is an integral multiple of Planck's constant upon 2 pi. So not every orbit is possible, and the ones which are possible have got multiples of h upon 2 pi amount of angular momentum. So we can see how Bohr had applied Planck's idea of quantization to the atom. Now, every orbit has a certain energy. So these are energy levels. So we see that this electron is at energy level 1 and this one is at energy level 2. The electron in the higher energy level can come to the lower energy level by radiating energy, which is exactly the difference between E2 and E1. Similarly, an electron in the lower energy level, which is E1 in this case, can go to the higher energy level, that is E2, but for that it will have to absorb energy, which is exactly the difference between E2 and E1. So the energy levels are discrete, and transitions between these energy levels cause radiation emission. And since energy levels are discrete, the energy emitted to photons is also discrete or quantized. Therefore, we see that Bohr was able to explain why atoms are stable, and he was also able to explain the quantized radiation from atoms. That is, radiation is not continuous. And he did that by using this assumption that angular momentum is an integral multiple of h upon 2 pi, that is, angular momentum is quantized. Now let's do some calculations. On the right hand side of this equation, we have the centripetal force felt by an electron. Mass here is m, mass of the electron. The v is for the velocity of the electron, and r is the radius or the distance between the nucleus and the revolving electron. So this would be the r. Note that we are trying to do these calculations for the hydrogen atom, which has just one proton in the nucleus and one electron revolving around it. So the charge of this is minus E and charge of this is E. Now this centripetal force is provided by the electrostatic attraction between the proton and the electron. Now Bohr told us or proposed that angular momentum, which is mvr, is quantized. So mvr is an integral multiple of Planck's constant on 2 pi. So n can be 1, 2, 3 and so on. If we get the value of v from the first equation and plug it into this second equation, we can get the radius of the nth orbit. So if you plug in different values of n equal to 1, 2, 3 in this equation and so on, you can get the radius of that particular orbit. Now let's talk about the energy of the electron. So the energy would be given by the sum of the kinetic energy and the potential energy. So if we put V here and we solve, we get The energy of the nth orbit is given by this relation, and R stands for this expression. Also, Bohr told us that when a transition happens between one energy level and another energy level, the energy of the radiation is the difference between those two energy levels. So we have that relation expressed here. R upon m square is the lower energy level and R upon n square is a higher energy level. This expression tells us the amount of energy that comes out whenever there's a transition from the nth energy level to the mth energy level. So if an electron comes down from n equal to 3 to n equal to 1, we can put it here. And using this, we can get the frequency of the radiation. So we see that Bohr was able to use the idea of quantization from Planck and Einstein and come up with a good explanation or a good theory regarding the structure of the atom, particularly the hydrogen atom. And now we come to a very interesting development. Louis de Broglie in 1924 wrote his PhD thesis, and in that thesis he proposed something very disruptive. He asked the question that if a photon can have wave and particle-like properties, can an electron also exhibit the same duality? And he extended this question further and asked whether all of matter shows both wave and particle-like phenomena. A very interesting question indeed. He started off with a theory from photons or light. He said if the momentum of a photon is given by E upon C, and we have seen that the energy of a photon or radiation is Planck's constant into its frequency, and C here is the speed of light or the speed of the photon, and we know that C equal to lambda into its frequency, where this is the wavelength. Therefore, if we combine this, we get that the momentum of the photon equal to Planck's constant divided by the wavelength of the photon. De Broglie proposed that if P equal to Planck's constant upon the wavelength is true for photons, then maybe it's true for all particles. So he gave this relation or proposed this relation to say that every material object is associated with a wave, and the wavelength of that is given by Planck's constant divided by the momentum of that particle or that object. This was indeed a dramatic and disruptive idea. What this means is, or what he proposed was, that every particle, everything around us, electron, photon, even things like chairs and tables and billiard balls, everything is both a particle and a wave, and the wavelength of that is given by this relationship. But is this actually true? In the year 1927, Davison and Germer, they did an experiment which showed that electrons also display diffraction, which is wave-like behavior. This experiment showed that electrons behave like both waves and particles, and the wavelength was exactly as proposed by de Broglie. Now, electrons and photons also behave like particles, and it was established earlier in 1923 by Compton. What Compton had done was to take electrons and strike them with X-rays. The results of this experiment could not be explained if we were to take both as waves. What he found was that the photons strike the electrons much like billiard balls do, and they just bounce off each other. This collision between a photon and electron is an elastic collision, and this shows that both of them are behaving like particles. So we see that photons have wave and particle-like properties. Similarly, electrons also have wave and particle-like properties. So what de Broglie was trying to say was more or less established that all of matter had wave and particle-like properties. Now this is a very interesting concept, and the question arises, if things around us are also behaving like waves and particles, why don't we see that wave-like behavior? So let's do some calculations to understand what kind of wavelength we would see for two different phenomena. One is an electron moving at 1/10 the speed of light, and a ball of 100 grams moving at 1 meter per second. So according to de Broglie, putting in the values, this is for the electron. This is Planck's constant, which is same for everything. The mass of the electron is 9×10⁻31. We are using some approximate values. And the speed of light is, and our electron is moving at 1/10 the speed of light. So if we simplify this, we get approximately, so the wavelength of an electron moving at 1/10 the speed of light is this much. Now let's do the same calculations for a ball of 100 grams moving at 1 meter per second. So the Planck's constant and mass of the ball is 1.1 kg, and it is moving at 1 meter per second. The result that we get now, if we look at the wavelength of this electron, now this is of the order of the size of the electron. The size of an atom is approximately, the size of the nucleus is approximately, so the electron's wavelength is of the same order as the atom, or in fact the electron itself. However, if you look at this ball moving at 1 meter per second, the wavelength is very, very small compared to the size of the ball. So the reason why we don't see wave-like behavior around us for everyday objects is because the wavelength is so small that it is impossible for us to observe it. Therefore, de Broglie was able to show that all matter has both wave and particle-like properties, and he was able to give us a expression or a formula to calculate the wavelength of these so-called matter waves. And we were able to experimentally confirm his theory, and we see that for everyday objects, the wavelength is so small that it cannot be observed. But for microscopic, or for objects which are of an atomic size or smaller than the atom, the wavelength is of the order of their size and therefore can be observed. Now let's briefly talk about the very famous Heisenberg's uncertainty principle. Classical mechanics or classical physics is completely deterministic. So when I use the word classical physics or classical mechanics, I refer to the physics before quantum mechanics. What this means is that if you know the position and the momentum of a system at any given time, you can predict how the system will evolve with complete accuracy. So classical physics is completely deterministic. You know the future if you know the present. However, quantum mechanics is not deterministic, or scientists found that determinism is broken in quantum mechanics. So waves are fuzzy, and we know that all matter has wave-like properties as well as particle-like properties. But waves are fuzzy, so it is not possible to completely determine the position of something if it is a wave. So Heisenberg proposed limits on the accuracy of measurements. So this was the Heisenberg's uncertainty principle, which he stated in 1927. What it says is that the uncertainty in the measurement of x, that is the position variable, and the uncertainty in the measurement of momentum follows this relationship. That is, when you multiply these two uncertainties, the result has to be equal to or greater than Planck's constant divided by 4 pi. So if you were to very precisely measure the position, then the momentum will become imprecise in order to satisfy this relationship. Similarly, if you were to measure the momentum with a high degree of accuracy, then the uncertainty will decrease in the measurement of momentum. So the uncertainty in the measurement of position will increase proportionally. This is easy to see. Let's say we have an electron and we want to measure its position. Now, how does one measure the position of something? We could shine some light on it, and when the light reflects back, we will know where that electron is placed. But in order to know the precise position of the electron, this light would have to be of small wavelength. Now, if the light is of a small wavelength, it would be of a high frequency. What this means is that since energy of the photon is, and if the frequency is high, then this means that the energy will also be large. So when we strike this electron with a photon of high energy, it would impart a large momentum to it. So we have measured the position of this electron with a high degree of certainty, but we have imparted a large amount of momentum, which is then difficult to measure. So we have measured the position of this electron, but the momentum has suddenly changed and we no longer know the momentum. Now this is a relationship between position and momentum. Similar relationships exist among other variables. So complementary variables are those variables which cannot be measured with arbitrary accuracy together. Another example is measurement of energy and the measurement of time also satisfies the same relationship. So we say that energy and time are complementary variables. There are many such complementary variables in quantum mechanics. So quantum mechanics is not a deterministic theory. In fact, it is a probabilistic theory, and we will discuss how to deal with probabilities in subsequent lectures. Now, since all matter is associated with waves, physicists try to form a wave equation which describes how a quantum system evolves. Schrodinger was able to propose this equation in 1925. It showed how a quantum system would evolve over time. This thing that we see here is a wave function. This contains all the information regarding the quantum system. So Schrodinger's equation proposed in 1925 was able to describe how a quantum system described by a wave function evolved in time. Now we see that there were many diverse ideas and theories around the middle of 1920s. But how do you make sense of it all? How do you combine all these ideas into a coherent theory? So Heisenberg, Born, and Jordan proposed something known as matrix mechanics in 1925. This was the first attempt to form a coherent theory based on all the ideas that were a part of quantum mechanics at that time. Schrodinger took a different line and proposed wave mechanics also in the mid-1920s. Schrodinger's wave mechanics was based on his wave equation, and matrix mechanics was based on transitions of states, for example, transitions of electrons from one state to another. In 1926, Schrodinger showed that both approaches, the matrix mechanics approach and the wave mechanics approach, are actually equivalent. So one could do quantum mechanics using either of these two methods and the results should be the same. So we see that around the mid 1920s, we were beginning to see a coherent theory of quantum mechanics, making sense of all the diverse ideas and experiments that existed at that point. Now let me describe briefly the journey of quantum mechanics from then on. So Pauli was able to apply quantum mechanics to the hydrogen atom in a much more coherent way, in a much more detailed way than Bohr had done earlier. Paul Dirac combined quantum mechanics and special relativity and came up with the theory of quantum electrodynamics. This happened in 1928. One of the predictions from this theory was antimatter. So Dirac proposed that an anti-electron, or what he named positron, should exist. And indeed, a positron or an anti-electron was discovered in the year 1932, which experimentally proved his theory. Dirac also proposed a mathematical structure for quantum mechanics. And we will talk about this mathematical structure in the future lectures. John von Neumann placed quantum mechanics on a rigorous mathematical basis. So John von Neumann used ideas of linear operators and Hilbert spaces and made a very coherent, mathematically sound theory of quantum mechanics. And this was in the beginning of 1930s. So quantum mechanics, a theory that was born in the year 1900, by the 1930s had a lot of experimental basis and it had a sound mathematical structure and it was coming alive. And this has been a very successful theory. It has been verified by numerous experiments. Till now, there has not been a single experiment that violates or casts any doubt on the validity of quantum mechanics. And quantum mechanics has a lot of strange predictions, and each one of them have been found true experimentally. So quantum mechanics is one of the most successful theories that we have ever had, and it is a very strange and very interesting theory. So this concludes our discussion on the beginnings of quantum mechanics. In the next lecture, we will talk about the central mystery of quantum mechanics. Thank you.